For nearly a century, physicists built their entire understanding of interstellar space on a simple, reasonable assumption that once you got far enough away from a star, the plasma filling the space between star systems should settle into something roughly uniform, a thin, steady, unchanging density that didn't much care how much farther out you traveled. It was a sensible assumption, built on solid theoretical grounds, and nobody had ever been able to test it directly because no instrument had ever actually traveled far enough into that environment to check. Then, a 50-year-old spacecraft launched during the Ford administration, running on a fraction of the power it takes to light a single room, kept flying, long after anyone expected it to still be transmitting anything at all, and started sending back numbers that didn't fit that assumption whatsoever. Not once, not as a fluke, over and over, year after year, as it continued its journey deeper into the space between the stars. Don Gurnett, the University of Iowa physicist who spent decades as the principal investigator on the instrument responsible for this discovery, put his own reaction to the data in blunt terms. He called it astonishing. This is the real story of what Voyager 2 actually found once it crossed into interstellar space, why the plasma density out there keeps rising instead of leveling off the way physics predicted, and why scientists still don't have a complete explanation for why. I'm your host, and this is your channel. If you want the real science behind the biggest surprises coming out of deep space, subscribe now, because we're just getting started. To understand why this finding genuinely startled the scientists studying it, you first need to understand exactly what Voyager 2 is, and how remarkable it is that it's still capable of measuring anything out there at all. It launched on August 20th, 1977, technically before its twin, Voyager 1, even though it carries the higher number, sent on a trajectory that took advantage of a rare planetary alignment occurring roughly once every 176 years, allowing it to visit Jupiter, Saturn, Uranus, and Neptune in a single continuous journey. To this day, it remains the only spacecraft in human history to have ever visited both of the solar system's ice giants. Its original mission was designed to last around 4 years. Instead, it kept traveling, and on November 5th, 2018, more than 41 years after launch, it crossed the heliopause, the boundary marking the true edge of our solar system, where the sun's constant outward stream of charged particles, the solar wind, finally loses its battle against the pressure of true interstellar space pressing in from the other side. That crossing made Voyager 2 only the second human-made object in history, after its twin, to leave the solar system entirely, and unlike Voyager 1, whose equivalent plasma instrument had been damaged decades earlier during a Saturn flyby, Voyager 2's plasma wave instrument was still fully functional, giving scientists a clean, direct, real-time confirmation of the crossing rather than an indirect, reconstructed one. That working instrument is exactly what made everything that followed possible. Voyager 2's plasma wave instrument doesn't measure density by directly counting particles the way you might expect. Instead, it listens for a very specific kind of electromagnetic signal called plasma oscillations, a natural vibration produced when an electron beam, typically generated by a shock wave moving through the surrounding medium, interacts with the ambient plasma. The specific frequency at which these oscillations occur is directly tied to the electron density of the plasma itself, meaning that by carefully measuring that frequency, researchers can calculate exactly how dense the surrounding interstellar material actually is at any given moment, even from a spacecraft sitting more than 11 billion miles away. When Voyager 2 first detected these plasma oscillations shortly after its 2018 crossing, on January 30th, 2019, the measured electron density came out to approximately 0.039 electrons per cubic centimeter. On its own, that number might sound almost meaninglessly small, but the significance lies in the comparison. Just inside the heliopause, in the outer reaches of our own solar system's protective bubble, typical plasma density measures around 0.002 electrons per cubic centimeter. The jump Voyager 2 measured crossing into true interstellar space represented roughly a 20-fold increase in density, a dramatic, unmistakable confirmation that the spacecraft really had crossed into a fundamentally different physical environment. And remarkably, that initial interstellar density reading closely matched what Voyager 1 had measured years earlier during its own 2013 crossing confirmation, a reassuring consistency that gave researchers real confidence in what both spacecraft were reporting. But here's where the story stops being a simple confirmation and starts becoming something genuinely unexpected. Because scientists didn't just want a single snapshot of interstellar density at the moment of crossing, they wanted to understand how that density behaved as both spacecraft continued traveling deeper into interstellar space over the following years. And what they found broke the assumption that had underpinned decades of theoretical modeling. Rather than leveling off into the kind of steady, uniform density most physicists expected true interstellar space to eventually settle into, the density kept climbing, continuously. As both Voyager 1 and Voyager 2 pushed further from the heliopause, their plasma wave instruments recorded a persistent, measurable increase in electron density, rising by nearly a factor of 2 within the first several astronomical units beyond the boundary, and then continuing to climb more gradually after that, reaching approximately 0. 12 electrons per cubic centimeter by the time the spacecraft had traveled out to roughly 160 astronomical units from the Sun. Gurnett, reflecting on what this pattern actually revealed about the fundamental nature of the boundary his instrument had helped confirm, offered a genuinely striking assessment. In a historical sense, he explained, the old idea that the solar wind would simply be gradually whittled away as a spacecraft traveled further into interstellar space turned out to be simply not true. What both Voyager spacecraft actually demonstrated, independently and consistently, was that there is a distinct, sharp boundary out there, not a slow, gradual fade from one environment into another. And reflecting on the broader physical implications of what his instrument had spent years measuring, Gurnett didn't hold back on how remarkable. He found the underlying physics to be, describing it as simply astonishing, how fluids, including plasmas, manage to form genuine, distinct boundaries under these conditions. The specific cause behind this rising density gradient remains, honestly, an area of active scientific investigation rather than a fully settled question, and it's worth being direct about that uncertainty rather than manufacturing false certainty. One leading theory proposes that interstellar magnetic field lines become increasingly compressed and strengthened as they drape directly over the outer boundary of our solar system's heliosphere, essentially wrapping around the bubble the way fabric might wrap around an obstacle. That compression, according to this theory, could generate a specific kind of instability, called an electromagnetic ion cyclotron instability, which has the effect of depleting plasma density in the immediate region where that draping occurs. Potentially helping explain the specific pattern of density changes researchers observed near the boundary itself. Supporting this general idea, Voyager 2 did in fact detect a notably stronger magnetic field than researchers had originally expected at the moment of its heliopause crossing, a finding consistent with genuine compression happening in that specific region of space. The mystery deepened further in the years that followed, adding real texture to what researchers already knew was a genuinely dynamic, non-uniform environment. In June of 2020, at a distance of roughly 124 astronomical units from the Sun, Voyager 2's plasma wave instrument detected something researchers explicitly connected to a very real physical event. An actual pressure front or shock wave moving through the local interstellar medium, likely triggered by intense solar activity that had occurred on our own Sun years earlier, its effects finally rippling outward across the vast distance separating the Sun from the spacecraft's current position. This event triggered a distinct, measurable jump in electron density, providing researchers with what one peer-reviewed study explicitly described as definitive evidence of a genuine radial density gradient in the very local interstellar medium, a real, physical, structured environment rather than the flat, featureless void that older models had assumed. Subsequent research tracking Voyager 1's data specifically noted that following a similar pressure pulse detected in 2020, at roughly 149 astronomical units from the Sun, density measurements appeared to level off at approximately 0. 147 electrons per cubic centimeter, suggesting the spacecraft may have finally reached a broad density peak, or possibly entered an entirely new physical regime that researchers are still working to characterize. What makes all of this genuinely significant, beyond the specific numbers themselves, is what it represents about the limits of theoretical modeling when it comes to environments no instrument had ever previously measured directly. For the entire history of astrophysics prior to these two spacecraft crossing the heliopause, every model of interstellar plasma density had been built from indirect observation, telescopes, mathematics, and careful theoretical extrapolation, informed by measurements of the interstellar medium taken from safely inside our own solar system's protective bubble, never from direct, sustained measurement taken from within that environment itself. When real spacecraft finally crossed that boundary and continued measuring the surrounding plasma for years afterward, the resulting data revealed a structured, dynamic, rising density gradient that the prevailing theoretical assumption of relative uniformity simply hadn't predicted. And this finding carries real weight for understanding something much closer to home. The heliopause functions as a genuine shield, deflecting a substantial portion of the most dangerous cosmic radiation, high-energy particles streaming outward from distant, long-exploded stars elsewhere in our galaxy, before that radiation can reach the inner solar system, including Earth, at full strength. If the interstellar environment pressing against that shield from the outside behaves in a more structured, denser, and more compressed way than existing models assumed, particularly right at the boundary itself, then questions about exactly how that shield holds up over the vast stretches of geological time genuinely deserve renewed, careful scientific attention, grounded now in real physical measurement rather than purely theoretical assumption. So here is where this actually leaves things, honestly, based entirely on published peer-reviewed research rather than exaggeration. Two aging spacecraft, both originally built to survive roughly 4 or 5 years, have spent more than a decade combined patiently measuring the density of interstellar plasma from a vantage point no other instrument in human history has ever occupied. What they found broke the standard assumption that this region of space should be relatively uniform, revealing instead a genuine, persistent density gradient that continues climbing as the spacecraft travel further from home, along with real physical evidence of actual pressure fronts and shock waves rippling through that environment years after their original solar trigger. The scientist who spent decades studying this exact instrument openly called the underlying physics astonishing, a word chosen deliberately by a researcher whose entire career has been built on careful, measured scientific language. That is not manufactured drama. That is the honest, documented reaction of the person who understood this data better than almost anyone else alive, describing what 2 dying, decades-old machines managed to teach us about the true structure of the space between the stars. If this kind of story is what you come here for, one grounded in real, published research rather than invention, hit subscribe and turn on notifications, because there's a lot more of the real universe left to explore. Drop a comment telling me what you think is really compressing that boundary out there, and share this with someone who still thinks the space between the stars is empty, uniform, and unchanging.